When Stephen Hawking stepped into the arena of black hole physics, he wasn't just trying to tweak a few equations or polish existing theories. He ended up doing something far more dramatic. He rewrote our understanding of some of the most mysterious objects in the universe. Before him, black holes were imagined as cosmic traps, regions where gravity was so strong that nothing, absolutely nothing, could escape once it crossed that invisible boundary called the event horizon. Not even light, the name black hole, itself almost dared scientists to accept that these objects swallowed everything and returned nothing. They were like cosmic one-way doors. But Hawking looked at black holes with a different kind of curiosity and a different set of tools. Other scientists saw a dead end. Hawking saw a crack in the wall, and through that crack he glimpsed one of the most revolutionary ideas in modern physics. Black holes can glow. Black holes can emit energy. Black holes aren't eternal prisons. They leak, they shrink, and they can even disappear over time. This phenomenon would eventually be called Hawking radiation, and it would ignite an intellectual explosion that is still shaping physics today. To understand why this idea was so shocking, you kind of need to understand the world Hawking stepped into. In the early 1970s, physicists were divided into two camps. On one side, you had general relativity, Einstein's monumental theory describing gravity as the curvature of spacetime. It handled massive objects, black holes, stars, galaxies, all the giant miracles of the cosmos. On the other side, there was quantum mechanics, the wild and unpredictable framework that governed the tiniest particles, electrons, quarks, photons, fields bubbling in the vacuum. The problem: these two theories hated each other. They didn't match, didn't cooperate, and they certainly didn't describe the same universe in the same way. Black holes sit right in the middle of this fight. They are massive, curved, spacetime objects, pure relativity territory. But they're also places where quantum effects should matter enormously. It's like placing a heavyweight boxer and a chess grandmaster on the same board and expecting them to play the same game. For decades, scientists basically tiptoed around this conflict, but not Hawking. He jumped right into the arena. Hawking began by studying black hole thermodynamics, a field that barely existed before he touched it. Physicists like Jacob Bekenstein had proposed something almost heretical. Maybe black holes have entropy. Maybe they aren't just empty pits in spacetime. Maybe they have a kind of disorder, a kind of information content. Hawking originally disagreed. In fact, he tried to prove Bekenstein wrong. But the deeper he went into the math, the more something unexpected started to appear. The vacuum of space, according to quantum mechanics, is never truly empty. It is always filled with tiny flickers of energy. Particles pop into existence and vanish again, like little flashes on an old TV screen. These are called virtual particles, and under normal conditions, they annihilate so quickly that they seem irrelevant. But something strange happens near the event horizon of a black hole. That edge of no return creates a boundary where the laws of quantum mechanics start behaving differently. Hawking realized that if a pair of virtual particles popped into existence right on the edge of a black hole, one particle could get sucked in while the other escaped. Normally, these particles destroy each other instantly when they collide. But if the event horizon pulls them apart, the escaping particle becomes real, something that can move outward into space. And because energy must be conserved, the black hole loses a tiny bit of energy every time this happens. Energy loss means mass loss, because Einstein told us E equals mc2, so the black hole shrinks, slowly, very slowly. But not zero, not impossible, not eternal. This was the moment the universe changed. Hawking published his work in 1974, and the reaction was electric. The idea that black holes emit radiation was so wild, so counterintuitive, that even Hawking himself was surprised. He often joked later that he wasn't trying to create a revolution. He was trying to prove someone else wrong, and accidentally stumbled upon one of the most important discoveries in cosmology. Hawking radiation became the missing bridge between quantum mechanics and general relativity, a rare place where the two pillars of physics actually talk to each other. And they don't whisper, they argue loudly. Hawking radiation shook the scientific world for another reason. It meant black holes aren't immortal. They don't last forever. Over unimaginable timescales, they evaporate. They shrink until they eventually vanish in a final burst of energy. That means black holes have lifespans, thermodynamic properties, temperatures, all things nobody expected. Before Hawking, nobody even imagined asking, "What's the temperature of a black hole?" After Hawking, that became a standard question in theoretical physics. This discovery also dragged physicists into one of the great wars of modern science, the information paradox. If a black hole evaporates and disappears, what happens to all the information it swallowed? Does it get destroyed? But quantum mechanics says information can never be destroyed. Relativity says the black hole can evaporate. So who's right? The answer is still being fought over today. Entire generations of physicists, from string theorists to quantum gravity researchers, are still trying to solve the puzzle Hawking created. His idea also led to a broader field of study, black hole thermodynamics, a deep relationship between gravity, entropy, information, and heat. It's one of the main reasons scientists now suspect that spacetime itself might have an atomic structure, tiny units of geometry that we haven't discovered yet. Hawking radiation hints that the universe might be far stranger than we imagined, with gravity emerging from deeper quantum realities. The elegance of Hawking radiation is that it connects things that should never meet. It uses quantum field theory, general relativity, thermodynamics, and information theory all at once. It's like a cosmic handshake between four giants of physics, mediated by a man who could barely move a muscle in his body, but could move the boundaries of human knowledge. What makes this discovery even more beautiful is the irony. The brightest idea about the darkest objects in the universe came from a man whose own physical world was collapsing. While it less slowly shut down Hawking's body, his intellect soared into regions no human mind had reached. Every new result, every prediction, every equation he produced pushed the boundaries of what scientists thought possible. And the universe seemed to respond. Hawking radiation became a foundational concept in modern physics, a doorway into the study of quantum gravity, string theory, holographic principles, and the nature of spacetime itself. Without Hawking, the entire landscape of theoretical physics today would look completely different. The reason his idea stands out isn't just because it was clever. It's because it changed the rules of the game. It forced scientists to ask questions they didn't even know existed. It created new fields, new theories, new technologies, and new dreams of understanding the cosmos. Hawking didn't just study black holes, he humanized them. He gave them temperature, personality, behavior. He turned them from silent cosmic vacuum cleaners into living, breathing participants in the thermodynamic drama of the universe. And he showed that even in the darkest places, there is light, literally. If you ever feel like the universe is too big, too complex, too impossible to understand, remember what Hawking showed us. Even the darkest objects can shine, and even the hardest problems can be Solved when you look at them from the right angle. Hawking's discovery didn't just push physics forward. It reshaped the entire conversation around the destiny of the universe. Before Hawking radiation entered the scene, black holes were seen as ultimate endpoints, cosmic erasers that swallowed information, matter, energy, and anything foolish enough to fall too close. They were the dragons at the edge of the cosmic map, places you point at and say, "Here be monsters." But after Hawking's calculations, black holes became dynamic entities with life cycles. They could gain mass, lose mass, heat up, cool down, and eventually they could die. That simple idea cracked open a whole swarm of deeper questions. One of the most fascinating aspects of Hawking radiance is how it forces us to rethink the relationship between the physical world and the informational world. In physics, information isn't just data. It's the specific arrangement of matter and energy. When a piece of paper burns, the pattern of ink is destroyed, but the information is preserved in the smoke, the ash, the heat released, and the molecules that scatter. Quantum mechanics insists on this. Information can be scrambled, mixed, disguised, transformed, but it can't disappear. Ever? Now picture a black hole swallowing stars, planets, atoms, photons, spacecrafts, maybe even civilizations over the scale of trillions of years. All that information falls in and gets trapped. Then imagine the black hole evaporates through Hawking radiation. The radiation is random, thermal, chaotic. It doesn't seem to carry any trace of the things that went in. You could throw in a diamond or a donut, a planet or a piano. The radiation would look identical. So where is the information? Did the black hole destroy it? That would break quantum mechanics. Did the information escape? Then how? And where? This is where Hawking's discovery detonated the black hole information paradox, one of the greatest unsolved mysteries of modern physics. Hawking originally believed that information was destroyed, not because he wanted to break physics, but because that's where the equations seemed to lead. Other physicists sharply disagreed. Decades later, after almost gladiator-level debates, Hawking himself changed his stance. He conceded that information must escape somehow, though the exact mechanism remains hidden. Today, the paradox has evolved into a playground for cutting-edge theories, holography, wormholes, quantum entanglement, string theory, emergent spacetime. It's all connected. Without Hawking's spark, none of these theories would have grown the way they have. But there's another layer of depth here. Hawking radiation isn't something we can easily observe. Black holes that are big, like those in galaxies, emit radiation so faint it's practically non-existent. The universe won't let us see the effect directly right now. But small black holes, the kind that might have formed in the early universe, would radiate much more intensely. If such primordial black holes existed, some might have already evaporated, leaving behind bursts of high-energy particles. Others, smaller ones, might even still be evaporating now. Scientists have set up detectors and telescopes, hoping to catch the final screams of a dying black hole, a signature of Hawking's theory. So far, nothing confirmed. But that only shows how far ahead Hawking was thinking. Even though we can't observe Hawking radiation directly yet, the theory is so mathematically elegant and so deeply woven into the structure of quantum field theory that most physicists accept it as real. It also appears in simulations of analog black holes, like special fluids, Bose-Einstein condensates, and optical fibers that mimic event horizons. Amazingly, these analog experiments have produced radiation that behaves exactly like Hawking predicted. It's not a cosmic black hole, but the physics matches. That's how powerful Hawking's idea is. It shows up everywhere, even in laboratory setups he never imagined. Let's zoom out for a second. What does it actually mean for a universe when black holes evaporate? Well, imagine the far, far future, longer than you can emotionally process. Stars die, galaxies drift apart, planets break down, and in the final chapters of cosmic time, only black holes remain. They are the last actors on the cosmic stage, and then, slowly, through Hawking radiation, they begin to disappear. First, the small ones die in explosive flares of energy, then the medium ones shrink. Finally, the giants, the supermassive black holes at galaxy centers, start their slow fade out. In the end, the universe becomes a cold, dark ocean with tiny ripples of radiation left behind, Hawking radiation. The echo of black holes that once shaped galaxies. Hawking didn't just explain black holes. He gave us a vision of the universe's final moments. That's the scale of his contribution. From the quantum dance of virtual particles to the entire cosmic timeline. Now, back to the heart of Hawking's original insight. The beauty of Hawking radiation lies in the mathematics. It's one of those rare theories where several different branches of physics all point to the same conclusion. If you approach the problem from quantum field theory, the vacuum fluctuations near an event horizon naturally produce radiation. If you approach the problem from thermodynamics, black holes having entropy implies they must have temperature, and temperature implies radiation. If you approach the problem from relativity, the event horizon is a boundary where quantum effects become amplified. Every pathway leads to the same answer: black holes radiate. This was shocking because before Hawking, everyone assumed black holes could only get bigger. If something fell into them, they gained mass. If they swallowed stars or gas clouds, they grew. There was no known process by which they could shrink. Hawking flipped that story. Suddenly, black holes were not infinite consumers. They were temporary objects governed by the same physical laws as everything else. They were mortal. This led scientists to ask, if black holes can evaporate, what does that say about gravity? Gravity is the weakest of all fundamental forces. Yet black holes trap everything, overpowering even light. If such superpowerful objects can slowly lose mass due to tiny quantum effects, that tells us there's a fragile balance between the cosmic and the microscopic. And inside that balance might lie the key to a theory of everything. Hawking radiation became a signpost pointing toward a deeper truth, that gravity might not be fundamental, that spacetime might not be smooth, that the universe's geometry might emerge from something more basic. This is where ideas like the holographic principle come in. The concept that the information inside a region of space might be stored on its boundary, like a cosmic hard drive. The mathematician Leonard Susskind and Hawking had long-standing debates about this. Their intellectual rivalry pushed the field forward in ways that shaped 21st century theoretical physics. And here's the most touching part. Hawking wasn't just doing physics in an abstract, isolated way. He was fighting a daily battle with ALS, a disease that was destroying his body even as his mind soared. His fingers weakened, his speech faded, his limbs refused to move, but his mind was radiating energy, pulling ideas from the universe itself. Every new discovery he made was a triumph over his own biology. Hawking radiation, in a way, is a metaphor for Hawking himself. Even in the presence of crushing gravity, even when trapped by physical limits, something brilliant escapes. Hawking's work also transformed how scientists think about the fabric of space itself. One surprising implication of Hawking radiation is that particle creation isn't special to black holes. It's a general feature of curved spacetime. That means the early universe, with its rapid inflation, extreme energy, and dramatic curvature, was filled with similar phenomena. This helps explain things like cosmic microwave background fluctuations, structure formation, and even the distribution of galaxies. The same math that explains why black holes evaporate also explains why the universe looks the way it does. Another deep consequence of Hawking's discovery is that it framed black holes as thermodynamic systems. This led to the famous black hole thermodynamics laws, which resemble the classical laws of thermodynamics, but in the language of spacetime. The event horizon has surface area like entropy, gravity mimics pressure, and Hawking temperature gives black holes a thermal identity. This viewpoint radically changed the philosophy of physics. Suddenly, the universe looked less like a cold geometric machine and more like a giant information processing system. In the decades following Hawking's breakthrough, physicists found echoes of his ideas everywhere. In 1997, Juan Maldacena introduced the AD-S/CFT correspondence, basically the idea that gravity in a space can be described by a quantum theory without gravity on the boundary of that space. This was the clearest evidence yet that information is never lost, even in a black hole. It also directly supports Hawking's later conclusion that black holes must preserve information after all. So whether you approach the universe from a quantum lens, a gravitational lens, or an informational lens, you run into Hawking's legacy every time. His theory is a lighthouse, illuminating the edges of what we know and hinting at what lies beyond. One of the most poetic aspects of Hawking radiation is that it shows how something incredibly small, a tiny quantum fluctuation, can determine the fate of something unbelievably massive. A universe-sized black hole weighing more than millions of suns can lose its mass one quantum at a time. It's like watching a mountain erode because of grains of sand blowing in the wind. This perfect unity between the small and the large, between the quantum and the cosmic, is what makes Hawking radiation such a masterpiece. Today, Hawking radiation isn't just a theory, it's a symbol. It stands for the idea that the universe is deeper than our first impressions, that even the darkest regions hide surprising light, that the impossible can be real under the right equations. Stephen Hawking didn't just explain black holes, he explained how to think about the universe. He showed us that the cosmos is not a cold, indifferent void. It's full of secret processes, invisible dances, and astonishing truths, waiting to be discovered by anyone bold enough to imagine them. And maybe that's the greatest part of his contribution. Hawking made the most mysterious objects in existence feel human. He turned black holes into storytellers, narrating a tale of information, energy, life, death, and rebirth. And he taught us that understanding the universe is not just a scientific quest, but a deeply human one. We wonder about black holes because we wonder about ourselves, where we came from, where we are going, and what happens in the end. Hawking radiation is more than a scientific idea. It's a beacon of curiosity, a challenge to assumptions, a reminder that even the deepest darkness can shine. And because of Stephen Hawking, the universe is brighter, both literally and metaphorically. Before Stephen Hawking arrived on the scene, cosmology was like a half-finished puzzle. Scientists knew pieces of the universe's story, the Big Bang, expanding space, scattered galaxies, strange cosmic background radiation, but they didn't have the full picture. Some pieces fit, others didn't, and the biggest questions were the ones nobody could answer. Why did the universe begin the way it did? What happened at the very start? How does space-time behave under extreme conditions? What is the universe actually made of? These questions lingered like mysteries, waiting for the right mind to crack open the deepest layers of the cosmos. Stephen Hawking became that mind. He stepped into cosmology with a mix of mathematical firepower and philosophical daring. Where others saw boundaries, points where equations break, where theories collapse, where logic fails, he saw pathways. Hawking didn't just do physics. He reinvented the way physicists talked about the universe itself. His ideas reshaped the entire understanding of cosmic origins, the structure of space and time, and the ultimate destiny of everything that exists. To understand his impact, you first need to know what cosmology looked like before Hawking. The Big Bang model was already accepted, but it was incomplete. It said the universe started from an extremely dense and hot state, and has been expanding ever since. But it didn't explain what happened at the very beginning, the first moments, the initial reasons, the deep mechanics of creation. It also didn't explain the structure of the universe on the largest scales. Why does it look so uniform? Why are galaxies arranged the way they are? Why is the cosmic microwave background so smooth? Why is space flat rather than curved? Theories existed, but they were fragile, disjointed, or mathematically unstable. Physicists knew the universe started somewhere, but they were afraid to look too close at the start, because the equations of general relativity exploded into nonsense. The laws of physics seemed to break down right where they mattered most, the moment of creation. This is where Hawking entered like a cosmic locksmith. Instead of accepting that the beginning was unknowable, he did the opposite. He aimed straight at the singularity. A singularity is a point where density becomes infinite. Spacetime bends into mathematical chaos, and the rules of physics simply stop working. The Big Bang Singularity was thought to be such a point, the first moment, of the universe where everything came from a single, infinitely dense point. But Hawking, together with mathematician Roger Penrose, discovered something transformative. Using advanced geometric methods and Einstein's equations, they proved that singularities weren't just accidents. They were inevitable. Under certain general conditions, if the universe was expanding today, then it must have come from a singular beginning. Their singularity theorems were groundbreaking because they made the Big Bang not just a hypothesis, but a mathematically unavoidable reality. It was the cosmic equivalent of saying, "There's no escape, the universe definitely had a beginning." This was like turning on a flashlight in a dark room. It gave shape to the concept of the universe's birth. Suddenly, cosmology had a firm foundation. The universe didn't just magically appear. It followed rules, deep rules, tied to the nature of spacetime itself. But Hawking wasn't done. If the universe came from a singularity, then what does that singularity look like? What does it mean for spacetime to emerge? Hawking realized that this is where quantum mechanics must step in. Einstein's relativity describes big things, galaxies, planets, spacetime geometry. Quantum mechanics describes small things, particles, fields, energies in the tiniest scales. But the beginning of the universe, that's the place where big and small collide. Hawking knew that to understand the origin of the universe, you needed a theory that combined both. And that's where Hawking made one of the biggest intellectual moves of the century. He applied quantum mechanics to the universe itself. This led him to ideas that were radical and almost poetic. One of the most transformative was the no-boundary proposal, often called the Hartle-Hawking state. This idea turns the origin of the universe into something smooth, elegant, and mind-bending. Hawking argued that before the Big Bang there was no time as we understand it. Time doesn't stretch backward forever, it curves. Just like how Earth has no edge. You don't fall off the planet by walking far enough. The universe has no temporal edge. Time near the beginning behaves like a spatial dimension. So instead of a hard beginning, the universe emerges smoothly, like the North Pole emerges from Earth's surface without any sharp border. This was a profound shift. Before Hawking, the universe began with a violent start. After Hawking, the universe became something that grew naturally from quantum geometry. No explosion, no boundary, no before. This idea doesn't just change the origin of the universe, it changes the philosophy of creation. It suggests the universe didn't need a prior cause, didn't require something else to start it. It simply emerged from physical laws themselves. Time began at the Big Bang in the same sense that latitude begins at the North Pole, not with a bang, but with a smooth starting point built into geometry. That's Hawking's genius, making the universe feel both more mysterious and more logical at the same time. But Hawking's influence doesn't stop at the beginning of time. He also reshaped how scientists think about the structure of the universe, how space, time, matter, and energy form the cosmic web we see today. For example, Hawking was one of the first to propose that tiny quantum fluctuations in the early universe could grow into the massive structures we see now. That means galaxies, galaxy clusters, cosmic voids, all of them may have been seeds that formed from microscopic jittering at the start of time. This idea became incredibly important when cosmic inflation theory emerged. Inflation says the universe expanded faster than the speed of light in its first fraction of a second. That would stretch tiny quantum fluctuations into large cosmic features. Hawking's work laid the mathematical groundwork for this, making him one of the silent architects behind the modern inflationary universe. And that's not all. Hawking made major contributions to how we understand the uniformity of cosmic microwave background radiation, the flatness of space, the geometry of early inflation, the statistical distribution of density in the universe, the role of quantum fields in shaping cosmic evolution. These ideas may sound technical, but they shape everything we know about the universe's large-scale structure. When you look at a photo of galaxies spread across billions of light years, those patterns trace back to Hawking's ideas about fluctuations and quantum origins. He also connected cosmology with the concept of entropy, the measure of disorder in a system. His work on black hole entropy showed that the universe as a whole might have an information-based structure. This became a stepping stone toward viewing the universe not just as a physical system, but as an information processing system, a radical, modern idea that influences theoretical physics, computer science, and even philosophy. One of the most beautiful aspects of Hawking's cosmology is that he didn't treat the universe as a cold machine. His work often hinted at something deeper, that the universe has a kind of elegance, a kind of self-consistency, a kind of mathematical poetry. He showed that the laws of physics aren't just arbitrary rules. They're intertwined in ways that reveal harmonies across scales. The tiniest quantum flicker influences the largest cosmic structure. The birth of time influences the heat of black holes. The way galaxies cluster connects back to the beginning of everything. Hawking changed the origin story of the universe not by rewriting everything, but by adding the missing chapters, the quantum chapters, the ones that explain the scenes before the opening act. He reshaped how we imagine the universe, not as a static thing, but as a dynamic event, a continuous creation, unfolding out of the laws of physics themselves. And he gave scientists the mathematical language to treat the universe as a quantum object. That's why Hawking stands as one of the greatest cosmologists in history. He didn't just explain cosmic origins, he rebuilt the entire concept from the ground up. And all this while fighting a disease that was shutting down his body. Yet his mind traveled further than telescopes could see and deeper than equations had ever been solved. His work didn't just describe the universe. It expanded it for science, for humanity, and for every mind curious enough to look up at the night sky. Think about it like having a supercomputer with powerful software installed, but none of it opened. The software is knowledge. Opening the apps is experience. Without launching the app, you can brag that your system is loaded, but it's useless. Experience is the double click that awakens the program. Take the example of courage. Plato said we may have an inner seed of the idea, but unless you've been scared, pushed, challenged, pressured, or forced to step up, courage stays just a pretty word. Experience gives it weight. It gives it emotional muscle memory. You know how some people talk bravely but freeze when real danger comes. They have the concept but not the experience. Without experience, knowledge has no teeth. Plato leaned toward the idea that true knowledge is internal, waiting to be remembered. But life teaches us that for many things, memory alone doesn't cut it. You need practice, mistakes, real encounters. Experience shapes not only how much you know, but how deeply you know it. The difference between a kid reading about heartbreak vs. someone who's lived it, that difference is exactly Plato's point amplified. Experience transforms knowledge into wisdom. 2. Experience builds judgment, and judgment builds reality. Plato often said that the senses are tricksters. But he also admitted that sensory experience teaches us patterns, and patterns teach us judgment. Judgment is basically, given what I know and what I've seen before, what should I do now? And here's where things get wild. Your judgment, shaped by your past experiences, literally creates your reality. Not reality in a mystical way, but in a practical way. Two people can face the exact same situation and walk away with totally different interpretations. Example, a business fails. One person says, "I'm not cut out for this." Another says, "Okay, that's round one. Now I know where I messed up." Same event, different experience, based judgments, different realities born. Plato said knowledge of the forms gives you access to an objective truth. Cool, but human lives run mostly on subjective truths, the truths we build from the stories we tell ourselves after every victory, failure, heartbreak, humiliation, or win. This doesn't contradict Plato. It expands his idea. Pure knowledge may come from reason, but living knowledge is sculpted by experience. Your experience forms your internal compass. That compass guides your actions. Your actions shape your world. The chain is unbreakable. 3. Experience teaches limits, and limits teach direction. Plato believed reason teaches you what is perfect. Experience teaches you what is possible. Life has this funny way of humbling all of us. You try something. You fail, you try again, you get a little better, you adjust. This cycle creates a map of your limits. But here's the twist. Limits aren't walls, they're signposts. Experience shows you what not to do. Reason shows you where to go. Together, they make you unstoppable. Plato's whole philosophy of education was exactly this blend. Reason tells you what the good life is. Experience tells you how humans actually behave. Wisdom is navigating the tension between the two. A king raised in a palace with tutors, books, and theory may know political philosophy. But a leader who grew up witnessing suffering, injustice, hunger, and power struggles understands human nature. Which one do you trust more? Plato argued for philosopher, kings, but even a philosopher, king needed decades of exposure, training, and lived experience. Experience builds humility. Humility builds clarity. Clarity builds strength. 4. Experience makes knowledge personal, and personal knowledge drives action. Here's a deep one. Knowledge becomes yours only when it connects with your story. If I tell you helping others is good, that's abstract. But if someone once helped you when you were broken, hungry, or lost, suddenly the idea becomes rooted. You feel it. Plato said knowledge of the good is universal, but modern understanding takes it further. The meaning of the good becomes personal depending on your journey. This is why a person who has known betrayal values loyalty more. Someone raised in chaos loves stability deeply. Someone who struggled financially respects money differently. Those who felt invisible crave recognition or kindness. Experience colors your world. It adds emotional ink to intellectual outlines. Knowledge that is merely known is weak. Knowledge that is felt becomes purpose. Purpose drives action. Action changes the world. So experience doesn't just shape your knowledge, it shapes who you become. 5. The tension between ideal and real. Plato's lifelong battle. One of the most fascinating parts of Plato's thought is this tension. The ideal world, perfect forms, universal truths, logic, mathematics, beauty. The real world, political chaos, imperfect humans, flawed systems, unpredictable events. Plato's life was proof that even he struggled with this. He watched Athens execute Socrates, the most rational man alive, because of politics and fear. This taught Plato something books alone couldn't. People don't always act according to truth. They act according to experience. This realization is what fueled his thinking. You can't teach people only ideas. You must also shape their experiences. A good society crafts both education and environment. This is why he designed his academy, not just a school, a training ground for mind plus experience. He believed that without proper experiences, even the smartest person becomes dangerous. Knowledge without character is a loaded gun. 6. The ethical angle. How experience shapes good and evil. Let's get into the moral side, because this is where Plato gets spicy. He believed nobody intentionally does evil. They just misunderstand what is truly good. Modern psychology actually supports this. People's moral behavior is 80% shaped by environment and experience. So, a child raised in violence may normalize violence. A child raised in fear may grow into manipulation. A child raised in greed learns to take. A child raised in kindness learns empathy. Plato said the soul naturally seeks the good, but experience can distort or clarify that path. This means your moral compass is not born accurate. It is calibrated by your life. Experience shapes ethics. Ethics shape decisions. Decisions shape destiny. In that sense, Plato was right but incomplete. Knowledge of good isn't enough. You must experience goodness to recognize it. Just like knowing sunlight exists is different from standing in it. 7. The political angle. Why leaders need experiential wisdom. Plato didn't trust democracy. Not because people were dumb, but because people were untrained. He believed leadership should be the final stage of a long journey. Philosophical study character. Building personal trials real. World training mastery of self. Why? Because experience protects society from dangerous leaders. A leader without experience is impulsive. A leader without suffering lacks empathy. A leader without challenge lacks resilience. A leader without education lacks vision. Plato insisted the ideal ruler must experience life from every angle: poverty, discipline, study, hardship, so they understand the people they rule. Experience creates perspective. Perspective prevents cruelty. This thinking influenced modern systems: civil service exams, professional training, leadership, hierarchies, long apprenticeships, merit-based governance. Plato basically said, a good leader needs a good mind shaped by good experiences. 8. Knowledge evolves because experience evolves. Here's a delicious philosophical loop. Reason gives us timeless truths. Experience gives us new interpretations. So knowledge never stays still. Plato's truth about the forms hasn't changed. But our experience of the world, science, technology, culture, psychology, keeps expanding, which updates our understanding of those truths. Example: the idea of justice survived 2,400 years. But what justice means has changed through experience: slavery, women's rights, civil rights, digital rights, globalism. The form stayed, the meaning grew richer. Experience adds layers to truth. In that way, knowledge is not static. It's alive, always breathing and shifting with generations. 9. The personal growth angle. Experience creates identity. Experience creates memory. Memory creates patterns. Patterns create personality. Personality creates values. Values create choices. Choices create life. Plato believed the soul pre-exists the body. Modern thought says the soul grows through the body, through experience. You become what you've survived, what you've learned, what you've endured, what you've enjoyed, what you've feared, what you've lost, what you've loved. Life writes on you. Experience tattoos the soul. Knowledge without experience is a blank notebook. Experience fills the pages. 10. The ultimate takeaway. The second keynote shows a powerful principle. You can have knowledge without experience, but you cannot have wisdom without experience. Plato gave us the concept. Life gives us the proof. Experience shapes perception, deepens understanding, forms judgment, builds ethics, fuels action, creates identity, molds leaders, stabilizes societies, transforms knowledge into wisdom. Plato believed knowledge of the ideal world is the highest truth. But even the highest truth is meaningless until a human being lives it, tests it, wrestles with it, and applies it. Stephen Hawking's A Brief History of Time isn't just a science book. It's one of the rare works that completely changed the relationship between ordinary people and the universe. Before the book came out in 1988, subjects like quantum mechanics, black holes, the Big Bang, time travel, unified theories, and the nature of space-time were mostly locked behind the high walls of academic science. Only physicists, researchers, and advanced students knew how to talk about these ideas, let alone understand them. Hawking shattered that wall. A Brief History of Time became a bridge, a connection between the most mind-bending scientific theories and the curiosity of everyday readers. Instead of turning science into something too difficult, Hawking turned it into a story. He explained the birth of the universe as if he were guiding the reader through a cosmic journey. He took ideas that normally required pages of equations and translated them into simple metaphors, real-world examples, clear logic, and vivid imagination. That's why millions of people who had never studied physics suddenly found themselves exploring black holes, bending time, and questioning the nature of reality. One of Hawking's greatest talents was his ability to simplify without oversimplifying. He never made the science childish or inaccurate. Instead, he stripped away the intimidating parts and presented the core ideas in a way that made readers feel smart, not confused. He invited them to think with him. He made them feel like the mysteries of the universe belonged to everyone, not just scientists. Before Hawking, Terms like singularity, event horizon, or space-time curvature sounded like something only a scientist could decode. After a brief history of time, these ideas became part of global conversation. They appeared in movies, school textbooks, documentaries, and casual discussions. This is a massive accomplishment. Very few scientists in history have managed to shape public understanding the way Hawking did. Another reason the book reached millions is Hawking's unique voice. He wrote with humor, curiosity, and honesty. Even while dealing with cosmic scales, he didn't lose the human touch. His personality comes through every page, gentle, playful, fascinated, and deeply philosophical. Readers didn't just learn science. They felt connected to the scientist behind the words. And let's not forget the emotional power behind the book. Hawking wrote it while living with ALS, a disease that gradually took away his ability to move and speak. Yet he continued to explore the universe with more energy than most fully healthy people. That contrast, a man physically trapped in a wheelchair but mentally soaring across galaxies, touched millions of hearts. It made the book feel not just intellectual, but inspirational. People weren't just reading science. They were witnessing the story of a human spirit refusing to be limited by anything. A Brief History of Time became a global bestseller, translated into more than 40 languages, selling tens of millions of copies. For a science book, that's unheard of. It stayed on bestseller lists for years and sparked a wave of interest in cosmology. Suddenly, big questions: where did we come from? What is time? What happens inside a black hole? Does the universe have an edge? It became questions everyday people felt empowered to ask. The book also changed how science was taught. Teachers, professors, and schools began using it as a starting point to inspire students. It opened the door for a whole new genre of popular science writing. Today, authors like Neil deGrasse Tyson, Brian Greene, Carlo Rovelli, and Michio Kaku walk through the door Hawking opened. Without a brief history of time, the modern public understanding of the universe would be very different. At its core, the book did something deeply philosophical. It reminded people that science is not just about equations, it is about wonder. Hawking reignited the childlike sense of curiosity we all carry. He encouraged readers to ask impossible questions and imagine unimaginable worlds. He helped people see the universe as a place filled with beauty, mystery, and meaning. The book's impact goes beyond education. It influenced culture. It appears in movies, TV shows, art, and music. It helped define Hawking as a global symbol of brilliance and determination. People who might never read a physics textbook still recognize the book's title and understand its significance. Reading A Brief History of Time feels like sitting beside Hawking as he points at the night sky and says, "Let me show you something amazing." And when readers finish the book, they walk away not just with new knowledge, but with a new way of seeing themselves in the universe. Millions of people around the world, scientists, writers, students, dreamers, and ordinary readers, have said that Hawking's book changed their perspective. Some were so inspired that they pursued careers in physics or astronomy. Others simply found comfort in understanding that the universe is vast, mysterious, and beautiful. In short, Hawking didn't just write a book, he democratized the cosmos. He took the most complex ideas humanity has ever created and placed them gently into the hands of everyday people. He showed them that curiosity is powerful, that understanding is possible, and that knowledge belongs to all of us. Because of A Brief History of Time, millions discovered that the universe isn't something to fear or ignore. It's something to explore. And that, more than anything, is why the book remains a masterpiece that shaped modern science culture forever. Stephen Hawking's life was a testament to the resilience of the human spirit, an inspiring example of how determination and curiosity can triumph over seemingly insurmountable obstacles. Diagnosed with amyotrophic lateral sclerosis at the young age of 21, he was given a prognosis of only a few years to live. ALS is a progressive neurodegenerative disease that gradually robs individuals of their ability to move, speak, and even breathe independently. For most, such a diagnosis would signify the end of an ambitious career, the abandonment of dreams, and a retreat from life's pursuits. Yet, for Stephen Hawking, it became a defining challenge that shaped his legacy and demonstrated the extraordinary capacity of human perseverance. From the outset, Hawking refused to let his illness dictate the course of his life. Instead of succumbing to despair, he dedicated himself more fervently to the study of the universe. His work in theoretical physics, cosmology, and black hole dynamics began during this period of personal struggle, and it is remarkable to consider that some of his most significant contributions emerged while his body was progressively weakening. His determination exemplifies a rare combination of intellectual brilliance and indomitable spirit. While his physical abilities were constrained, his mind soared to explore concepts that stretched the boundaries of human understanding. Hawking's groundbreaking research includes his work on black holes, the nature of time, and the origins of the universe. Perhaps one of his most revolutionary discoveries was that black holes are not entirely black, but emit radiation now known as Hawking radiation, a concept that challenged the prevailing theories of physics and provided a bridge between quantum mechanics and general relativity. The rigor and originality of his work earned him recognition as one of the most influential scientists of his generation. What makes these achievements even more remarkable is the fact that he conducted much of this work while grappling with severe physical limitations. He wrote, lectured, and communicated complex theories through a speech-generating device, relying on a computer system controlled by the slightest movement of his cheek. This adaptation highlights not only his resourcefulness, but also his refusal to let the disease silence his ideas. Beyond his academic contributions, Hawking became a symbol of hope and inspiration worldwide. He showed that a debilitating condition did not equate to the end of one's potential. Millions admired him not just for his intellect, but for the courage and perseverance with which he approached life. Hawking's presence in public life, whether through lectures, interviews, or appearances in popular media, demonstrated that one could live fully, passionately, and meaningfully even in the face of tremendous adversity. In doing so, he redefined the boundaries of what is possible for individuals with disabilities, encouraging others to pursue their ambitions regardless of the challenges they face. Moreover, Hawking's story resonates because it bridges the personal and the universal. His battle with ALS was intensely personal, yet his achievements addressed questions that have fascinated humanity for centuries. How did the universe begin? What governs its evolution? What is the ultimate fate of space and time? By engaging with such profound inquiries, he invited the world to explore these mysteries alongside him, making the pursuit of knowledge a shared, collective endeavor. The courage he displayed in continuing his work, despite severe physical limitations, underscored the message that intellectual and creative contributions are not confined by bodily constraints. His life also emphasizes the importance of adaptability and innovation in overcoming obstacles. The technology that enabled him to communicate complex scientific ideas, despite his paralysis, is a testament to human ingenuity. Hawking did not allow the limitations of his body to become a barrier to his intellectual exploration. Instead, he embraced new methods, tools, and technologies to continue his research and connect with the world. This proactive approach to problem solving serves as a powerful lesson for anyone facing adversity. Solutions often exist, but they require determination, creativity, and the willingness to adapt. Furthermore, Hawking's perseverance inspired countless individuals outside the realm of science. His life story has motivated people across diverse fields, students, professionals, artists, and activists, to persist in the pursuit of their dreams, regardless of the obstacles they encounter. He became a beacon of hope for those living with chronic illnesses or disabilities, proving that physical limitations do not define one's ability to make meaningful contributions to society or to achieve greatness. In reflecting on Stephen Hawking's legacy, it becomes clear that his influence extends far beyond his scientific discoveries. While his work transformed our understanding of the universe, his life exemplified qualities that resonate universally: courage in adversity, dedication to one's passions, and the refusal to accept limitations imposed by circumstance. He demonstrated that the human mind, fueled by curiosity and resilience, can transcend even the harshest physical constraints. Ultimately, Stephen Hawking's ability to pursue groundbreaking research despite ALS is a story of triumph, inspiration, and the boundless potential of the human spirit. It reminds us that adversity, no matter how formidable, can become a catalyst for extraordinary achievement when met with determination, creativity, and unwavering hope. His life continues to inspire scientists, scholars, and dreamers worldwide, encouraging them to explore the unknown, challenge assumptions, and pursue their ambitions with relentless passion. Hawking's journey is a profound reminder that the pursuit of knowledge and the drive to make a difference are not hindered by physical limitations. They are fueled by the courage to persevere, curiosity to question, and the vision to see beyond the constraints of the present. Stephen Hawking's contributions to quantum, gravity, and cosmology represent some of the most profound advances in our understanding of the universe in the 20th and 21st centuries. While his physical body was gradually debilitated by amyotrophic lateral sclerosis, his mind was extraordinarily active, constantly probing the fundamental questions of space, time, and the origins of the cosmos. His work not only reshaped theoretical physics, but also bridged previously separate realms of scientific inquiry, providing a deeper understanding of the universe's structure and behavior. One of Hawking's central contributions lies in the study of black holes, regions of space where gravity is so intense that nothing, not even light, can escape. For decades, black holes were considered enigmatic and impenetrable objects within general relativity. Hawking's insight was to apply principles of quantum mechanics to these extreme gravitational environments, leading to the revolutionary discovery now known as Hawking radiation. This finding demonstrated that black holes are not completely black but emit radiation due to quantum effects near the event horizon, the boundary beyond which nothing can return. This breakthrough bridged the gap between quantum mechanics and general relativity, two pillars of modern physics that had previously been difficult to reconcile. It showed that black holes are dynamic, evolving entities rather than static, eternal objects, a perspective that fundamentally altered cosmology and our understanding of the universe's evolution. Hawking's work also extended to the concept of the origin of the universe and the nature of singularities. Alongside Roger Penrose, he demonstrated that under certain conditions, the equations of general relativity predict singularities, points where density becomes infinite and the laws of physics as we know them break down. This was a pivotal insight for cosmology, providing a rigorous mathematical framework for the idea that the universe began with a singularity, commonly associated with the Big Bang. Their work revealed that the universe is not static and eternal, but has a finite beginning, fundamentally influencing how scientists conceptualize the evolution of space-time. Another key aspect of Hawking's contributions is his exploration of quantum cosmology, the study of the universe at the intersection of quantum mechanics and general relativity. He proposed the no-boundary hypothesis with James Hartle, a groundbreaking idea suggesting that the universe has no initial singularity or boundary in imaginary time. In simpler terms, this model implies that the universe is self-contained, finite, and without a singular starting point, challenging traditional notions of a temporal beginning. This idea not only advances theoretical physics, but also provides a framework for understanding the universe's large-scale structure and evolution. It represents a profound shift in how scientists think about time, causality, and the very concept of creation itself. Hawking's approach was notable not only for its originality, but also for its mathematical rigor and physical intuition. He combined sophisticated theoretical techniques from quantum field theory, general relativity, and statistical mechanics to tackle problems previously considered intractable. His work on black hole thermodynamics, for instance, demonstrated that black holes have entropy and temperature, concepts that tie the gravitational, quantum, and thermodynamic properties of the universe together. This insight has far-reaching implications for understanding the fundamental laws governing the cosmos, and provides a pathway toward a unified theory of physics, a long-sought goal of scientists for decades. Importantly, Hawking's contributions were not confined to abstract theory. They also had a profound influence on how scientists model the evolution of the universe. His work laid the foundations for understanding cosmic inflation, the rapid expansion of the early universe, and the formation of large-scale structures such as galaxies and galaxy clusters. By exploring the interface between quantum mechanics and gravitational dynamics, he helped shape modern cosmology, providing tools and concepts that are now standard in theoretical physics. His research encouraged generations of scientists to explore bold ideas and to apply rigorous mathematical reasoning to questions that once seemed beyond the reach of human understanding. Beyond his technical achievements, Hawking's work in quantum gravity and cosmology is remarkable for its visionary scope. He asked fundamental questions about the origin, structure, and ultimate fate of the universe, questions that touch not only physics, but philosophy and human curiosity itself. His research invited scientists and the public alike to consider the universe not as a static backdrop, but as a dynamic, evolving system governed by profound physical laws. By doing so, he transformed cosmology from a largely descriptive science into a predictive, mathematically grounded discipline capable of addressing the deepest mysteries of existence. Hawking also influenced the scientific community through his commitment to communication and collaboration. Despite his physical limitations, he engaged with other researchers, sharing ideas and fostering discussions that pushed the boundaries of theoretical physics. His work inspired countless scientists to investigate the connections between quantum mechanics, gravity, and cosmology, sparking ongoing research into quantum gravity, string theory, and the multiverse. In this way, his contributions extend far beyond his own papers. They catalyzed a broader movement of inquiry and innovation that continues to shape the field today. In summary, Stephen Hawking's contributions to quantum, gravity, and cosmology represent a remarkable blend of intellectual creativity, mathematical precision, and visionary thinking. Through his discoveries, including Hawking radiation, the study of singularities, the no-boundary hypothesis, and black hole thermodynamics, he provided new frameworks for understanding the universe from its earliest moments to its farthest reaches. He demonstrated how quantum mechanics and general relativity can be integrated to explore some of the universe's deepest mysteries, leaving an enduring legacy that continues to guide contemporary research. Beyond his scientific achievements, his work embodies the power of human curiosity and determination, showing that the pursuit of knowledge can transcend physical limitations and inspire generations to explore the cosmos with wonder and rigor. Stephen Hawking's life and achievements extended far beyond the realm of theoretical physics, making him a global symbol of determination, intellect, and curiosity. While he is celebrated for his groundbreaking contributions to cosmology and quantum gravity, his enduring influence lies not only in his scientific discoveries, but also in the way he faced extraordinary personal challenges with courage, resilience, and an unyielding desire to understand the universe. Hawking's story has inspired millions worldwide, illustrating how intellectual passion combined with determination can overcome even the most formidable obstacles. Sclerosis at a GE21, Hawking confronted a disease that gradually robbed him of mobility, speech, and many basic physical abilities. Despite this prognosis, which most would consider devastating, he continued his academic work with unwavering determination. His ability to maintain focus, curiosity, and productivity in the face of such adversity made him an icon of human resilience. Hawking did not allow his illness to define him. Instead, he defined himself by the scope of his ambitions and the depth of his intellect. In doing so, he showed the world that determination is not measured by physical ability, but by the strength of one's will and the commitment to one's passions. Hawking's intellect was extraordinary, allowing him to grapple with some of the most challenging questions about the universe. He explored the origins of time, the behavior of black holes, and the fundamental laws that govern the cosmos, producing work that continues to shape modern theoretical physics. What made his intellect even more remarkable was his ability to communicate these complex ideas to the public in an accessible way. Through books like A Brief History of Time, public lectures, and media appearances, Hawking brought advanced scientific concepts into the mainstream, fostering a global appreciation for the wonders of the universe. His combination of deep knowledge and clarity of expression turned him into a symbol not only of scientific achievement, but also of intellectual accessibility. Curiosity was another defining feature of Hawking's life. Despite his physical limitations, he never lost his fascination with the universe or his desire to question, explore, and understand. His curiosity extended to both the scientific and the philosophical. He pondered not only how the universe works, but why it exists and what it means for humanity. Hawking's willingness to ask profound questions, often pushing the boundaries of current scientific understanding, inspired countless individuals to think boldly and challenge conventional wisdom. He demonstrated that curiosity is a driving force that can lead to extraordinary discoveries, and that the pursuit of knowledge is a lifelong endeavor that transcends personal limitations. Hawking's status as a global symbol was also reinforced by his public presence. He appeared in television shows, documentaries, and even popular media like The Simpsons and Star Trek, demonstrating that science can be both profound and approachable. He became recognizable not just for his wheelchair or his speech-generating device, but for the brilliance of his ideas and the courage with which he lived his life. This visibility allowed him to connect with audiences worldwide, becoming a source of inspiration for people of all ages and backgrounds. For many, Hawking embodied the idea that intellectual achievement and human resilience are qualities worth celebrating and emulating. In addition, Hawking's life symbolized the triumph of the mind over the body. ALS limited his physical capabilities, but it could not constrain his imagination, creativity, or intellectual contributions. He showed that the human spirit and intellect are capable of transcending physical challenges, a message that resonated globally and particularly among individuals with disabilities or chronic illnesses. Hawking's example challenged societal assumptions about ability, demonstrating that brilliance, creativity, and determination can flourish under circumstances that might seem insurmountable. Furthermore, Hawking's legacy extends to education and the promotion of scientific literacy. By engaging with the public and popularizing complex scientific ideas, he encouraged curiosity and critical thinking around the world. His lectures, interviews, and publications helped inspire a generation of students to pursue careers in science, mathematics, and technology. In this way, his influence was not confined to theoretical physics. It reached into classrooms, homes, and communities worldwide, cultivating a global culture of intellectual curiosity and appreciation for science. Hawking's global symbolic status is also tied to his ability to inspire hope. He faced profound physical limitations and a terminal illness, yet he lived a full and impactful life, traveling, teaching, and contributing to science until his death at the age of 76. His perseverance in the face of adversity became a narrative that transcended science, speaking to universal themes of resilience, courage, and the pursuit of excellence. Millions saw in Hawking a figure who refused to be defined by circumstance, demonstrating that the human capacity for determination and curiosity is limitless. Ultimately, Stephen Hawking's life exemplifies the power of intellect, determination, and curiosity to inspire and transform the world. His contributions to science are monumental, but equally important is the example he set through his personal journey. Hawking became a global symbol because he embodied the qualities that humanity admires most: the courage to face adversity, the brilliance to explore the unknown, and the insatiable curiosity to seek understanding, because in wartime, courage of morale knowledge becomes a battlefield in itself. Through his life and work, Stephen Hawking continues to inspire scientists, students, and dreamers alike. He demonstrated that physical limitations do not define human potential, and that the pursuit of knowledge, guided by curiosity and determination, can illuminate not only the mysteries of the universe, but also the limitless capacities of the human spirit. His legacy as a global symbol endures, reminding the world that with intellect, determination, and curiosity, individuals can overcome incredible challenges, make profound contributions, and inspire generations to reach for the stars both literally and figuratively. Stephen Hawking's contributions to physics and cosmology have left a profound and enduring impact on modern science, influencing the direction of research, shaping theoretical frameworks, and inspiring a new generation of physicists and space scientists. His groundbreaking work on black holes, quantum mechanics, and the nature of the universe continues to serve as a foundation for ongoing investigations into some of the most fundamental questions about the cosmos. Even after his passing, Hawking's insights guide researchers who are attempting to uncover the deepest mysteries of space, time, and the origins of the universe. One of the most significant aspects of Hawking's legacy is his work on black holes. Before his research, black holes were often viewed as simple, static objects, regions of space, where gravity was so intense that nothing could escape. Hawking's revelation that black holes emit radiation, now called Hawking radiation, fundamentally changed this perspective. This discovery suggested that black holes are not eternal, immutable entities, but dynamic systems that evolve over time. Hawking's work on black hole thermodynamics, entropy, and quantum effects has become central to modern theoretical physics, providing a critical bridge between quantum mechanics and general relativity. Researchers continue to build on these concepts in the quest for a unified theory of physics, exploring the connections between gravity, quantum theory, and the fundamental forces that govern the universe. Hawking also made substantial contributions to cosmology, particularly regarding the origin and evolution of the universe. His work with Roger Penrose on singularity theorems provided a rigorous mathematical framework for understanding the conditions under which the universe began. The no-boundary proposal, developed with James Hartle, offered a novel perspective on the universe's origin, suggesting that time itself could have a beginning without a boundary or singularity in imaginary time. These ideas continue to influence modern cosmology, guiding research into the early universe, cosmic inflation, and the structure of space-time. Scientists rely on these frameworks to model the formation of galaxies, stars, and other large-scale structures in the universe, allowing them to test theoretical predictions against observational data. Beyond theoretical advances, Hawking's work has practical implications for future space research. Understanding black holes, gravitational waves, and quantum cosmology provides crucial insight into phenomena that scientists aim to observe with advanced telescopes and space missions. For instance, his predictions about Hawking radiation inform the search for high-energy particles and radiation emitted by black holes. Observatories and satellites, such as the James Webb Space Telescope and upcoming black hole imaging projects, continue to explore these predictions, expanding our understanding of extreme environments in the universe. Hawking's theoretical models serve as guideposts for designing experiments, interpreting data, and framing questions about the cosmos that may one day be answered through direct observation. Hawking's work also inspires research into the fundamental nature of space and time, a topic that is central to the development of futuristic space technologies and interstellar exploration. By investigating the conditions of the early universe, singularities, and quantum effects on cosmic scales, scientists gain insights into the limits of space travel, the behavior of matter under extreme conditions, and the potential for future technologies based on gravitational or quantum phenomena. His theories influence not only abstract theoretical physics, but also practical considerations for humanity's long-term exploration of space, from understanding black holes' hazards to predicting the behavior of cosmic radiation in deep space environments. Moreover, Hawking's influence extends to the next generation of physicists and cosmologists. His life and work serve as an educational foundation for researchers who study quantum gravity, string theory, multiverse hypotheses, and the physics of black holes and neutron stars. Universities, research institutes, and scientific communities worldwide continue to build curricula and research programs based on his theories, ensuring that his intellectual legacy remains central to scientific progress. Students and researchers are encouraged to think boldly, challenge assumptions, and pursue innovative solutions to some of the most complex questions in physics, a mindset directly inspired by Hawking's example. Hawking's influence is also visible in the growing interdisciplinary integration of science. His work demonstrated that breakthroughs in physics often arise from combining insights across fields: quantum mechanics, relativity, thermodynamics, and cosmology. Modern research in astrophysics, particle physics, and space science increasingly reflects this integrative approach, which Hawking championed. By showing how theoretical predictions can inform observational studies, he helped establish a paradigm in which theory and experiment work together to expand knowledge, a model that continues to guide research in laboratories, observatories, and space missions. Importantly, Hawking's work has cultural and inspirational significance beyond the scientific community. His achievements demonstrate that even immense physical limitations cannot hinder the pursuit of knowledge and discovery. This message resonates with scientists, students, policymakers, and space enthusiasts alike, motivating collaborative efforts in space exploration, physics research, and STEM education. Public interest in space, cosmology, and black holes has surged partly due to Hawking's ability to communicate complex ideas effectively, inspiring broader engagement with science and ensuring that future research is supported by a curious and informed global community. In conclusion, Stephen Hawking's work continues to guide modern physics and future space research in multiple, profound ways. His discoveries in black hole thermodynamics, singularities, quantum cosmology, and the no-boundary hypothesis have reshaped theoretical physics and cosmology, providing models and frameworks that scientists continue to explore and test. Beyond theory, his insights inform observational research, guide space exploration projects, and inspire innovative approaches to understanding the universe. Hawking's intellectual contributions, combined with his resilience and ability to communicate complex ideas, ensure that his legacy remains central to scientific inquiry. His work continues to illuminate the path forward, encouraging humanity to explore the cosmos with rigor, curiosity, and imagination, ensuring that the mysteries of the universe remain within our reach for generations to come.